Alrighty, so these are kind of funky little problems. They're sort of related to refraction because they deal with um, waves traveling at different speeds in different media, right? So the notion here is that we've got water, right? We've got air, and the speed of sound in air is it pokes along at about 343 meters per second, right? In the water, it goes much faster. The speed of sound is 1,498 meters per second. So if you're here, let's imagine that you're swimming here, right? You're like, whoop, whoop, and somebody, I don't know, lights a firecracker right there. You're going to hear two little pows, right? One happens through the water, one happens through the air. And of course, the one that happens through the water is going to happen, you're going to hear that much sooner because it's going so much faster. Okay, so what time does it take the sound to reach you in the air? Well, that's easy, right? We are 1,250 meters away, right? So in the air, it's going to take 1,250 divided by 343. Okay, that's pretty simple math here. These problems can get a little bit tricky, so I'll show you how to set up the kind that's like on the FA. Okay, so well, what's interesting too, by the way, is that geologists use the fact that the waves travel at different speeds in different layers of rock, and they use that to actually do imaging and do calculations and stuff. But anyway, 1250 divided by 343. This is 3.644 seconds. 6443, I'll say, right? Okay, so that's how long it takes through the air. Through the water, it is much faster. 1250 divided by the speed in water, which is, I've been accused of saying water, so I'm trying to say water. 1250 divided by 1498. This is lickety split, so 0.83444 seconds. And that's the time through the water. Now, the difference, the delay is this, okay? The delay is 3.6443 minus 0.8344. So if I subtract those two numbers, minus this, I get 2.81 seconds. Okay? Now, the farther away this person is, or this explosion is, the bigger that gap is, just because it's like a race, okay? This is a real fast runner, this is a real slow runner, and they're going to be more spread out, okay? So let's do a different problem, right? Let's imagine that somebody gives you a problem that they say, okay, now we hear a delay of 3 seconds. Okay, there's an explosion there. We don't know how far this distance is, but you're here, right? And you hear a 3-second delay between the sound in the air, where the velocity is 343, and the sound in the water, where it's 1498, right? And there's a 3-second delay, so what is that distance? Well, it seems like you can't do this, but you can. Let me just show you, okay? What you do is you just set up an equation. So you go like this. You go whatever that x is divided by 343 minus whatever that x is divided by 1498. That is 3 seconds. Okay? And that can be solved. I know there's two x's there, but they're the same x, right? So you can factor that out, right? So you can say x outside of 343 minus 1 over 1498 equals 3, right? And then what can you do? I guess you go 3 divided by this, right? So I'm just going to go 3 divided by the quantity, 1 divided by 343 minus 1 divided by 1498. And I get 1334 meters, which is farther than the 1250 that resulted in only a 2.81 second difference. Okay, so the farther it is away, the bigger that time lag will be. And that's how you solve those. Those are cute little problems. Anyway, Thank you for entering the blue pen land to find some answers.